In this project, the airflow around a drone is simulated. UAVs can be considered as small drones. One of the most important advantages of drones is their remote control capability, which has made it particularly popular in the aviation industry and in the military industry also. The design of UAVs requires special care and consideration due to the fact that the flight as well as the control of the continuation of the flight in the drones is done through remote control commands. There has been a lot of effort to pay special attention to the structural design of these aircraft in terms of aerodynamics. Simulating the airflow around a UAV is crucial to studying aerodynamic forces and stability, and ultimately good design. Using simulation software such as ANSYS can significantly reduce the costs of design, construction, and testing of these complicated structures. In this project, the airflow around a drone is simulated due to the high speed of airflow during flight and also the possibility of very high separation in such flows. The standard k-epsilon model with the use of a standard valve function is exploited to analyze the turbulence of the airflow and to better investigate the separation of the current and flow from the surface. Considering the high sensitivity in the design of the drone's body, the initial geometry required for this analysis was created in CATIA software and completed in Gambit and also meshed inside Gambit too. The mesh type used for this geometry is unstructured. There are several assumptions that are considered that shows that this simulation is done using pressure-based solver. The present simulation and its results are considered to be steady and do not change as a function of time. Also, the effect of gravity has not been taken into account. From the scale mesh section, we can check the dimensions in all three directions and also view the length unit that is in meter in this CFD simulation. Also, via the mesh display section, we can display all the surfaces in the computational domain, including inlets, outlets, walls, and symmetry, and so on. For the turbulent equation, we select the standard k-epsilon model. The two-equation turbulence model allows the determination of both a turbulent length and time scale by solving two separate transport equations. The standard model in ANSYS Fluent falls within this class of models and has become the workhorse of practical engineering flow calculation in the time. Robustness, economy, and reasonable accuracy for a wide range of turbulent flows explain its popularity in industrial flow and heat transfer simulations. Also, it is a semi-empirical model. The standard model is a model based on a model transport equations for the turbulent kinetic energy, K, and its dissipation rate, epsilon. The model transport equation is derived from the exact equation, while the model transport equation for epsilon was obtained using physical reasoning. The k-epsilon standard model is a model based on model transport equation for the turbulent kinetic energy K and its dissipation rate, that is epsilon. The model transport equation for K is derived from the exact equation, while the model transport equation for epsilon was obtained using physical reasoning. In the derivation of the standard model k-epsilon, the assumption is that the flow is fully turbulent and the effects of molecular viscosity are negligible. The standard k-epsilon model is therefore valid only for fully turbulent flows. And finally, in the near wall treatment, we choose a standard wall function. If the k-epsilon turbulence model is used for the simulation, it is not possible to simulate flow vortex near the walls. A wall function must be defined to investigate the fluid behavior near the wall. So we should select one of these options. These wall functions are near wall analytical flow profiles obtained by explicitly solving the near wall flow equations. So they are more accurate than numerical methods, of course in simpler models, I mean. Also because of the need for no accurate mesh near the wall, like in this simulation that near wall meshes are not so more accurate than other meshes. They greatly reduce the computational time. So we choose the standard wall function for reduce the computational time. It should be noted that when using the k-epsilon model, due to the lack of accurate mesh near the walls, it is necessary to check the wall functions using y plus. And the suitable y plus should be between 30 and 300 for the standard model. Two default materials are identified for the fluid and also for the solid, that are air and aluminum respectively. From the material section, we can check all the material properties. The operating pressure is equal to the atmospheric pressure in the operating condition section. Pressure outlet boundary condition type has been specified for the outlet boundary, and also the gauge pressure is equal to 0. The UAV external surfaces are assumed as a stationary wall with no slip. Also, the velocity inlet boundary condition type has been selected for the inlet boundary, and the velocity magnitude is equal to 30 meter per second, and the direction is normal to the boundary. And finally, the walls of the wind tunnel are assumed to be a stationary wall with no slip. In the method part, we should define the pressure-velocity coupling that contains settings for pressure-velocity coupling schemes. For the pressure-based solver only, the scheme provides a drop-down list of the available pressure-velocity coupling schemes like simple, simple C, piezo, and coupled. In this case, in this CFD simulation, we set the scheme as a simple method. The pressure-based solver allows you to solve your flow problem in either a segregated or coupled manner. As you know, the simple is the segregated manner. ANSYS Fluent provides the option to choose among many pressure velocity coupling algorithms like simple C, piezo, and coupled. The simple algorithm that is used in this CFD simulation uses a relationship between velocity and pressure correction to enforce mass conservation and to obtain the pressure field. So the pressure velocity coupling scheme controls the manner in which pressure and velocity are updated when the pressure-based solver is used. The scheme can be either segregated, that means the pressure and velocity are updated separately, or to be coupled, that means the pressure and velocity are updated simultaneously. ANSYS Fluent provides the following segregated types of algorithms that are simple C, and piezo. In general, segregated methods like symbol that is used in this model are faster per iteration, while the coupled algorithm usually requires fewer iterations to converge. Spatial discretization, in summary, while the first order discretization generally yields better convergence than the second order scheme, it generally will yield less accurate results, especially on tree and tet meshes. For most cases, you will be able to use the second order scheme for the start of the calculation. In some cases, however, you may need to start with the first order scheme and then switch to the second order scheme after a few iterations. For example, if you are running a high Mach number flow calculation that has an initial solution much different than the expected final solution, you will usually need to perform a few iterations with the first order scheme and then turn on the second order scheme and continue the calculation to converge, to obtain the convergence exactly. Alternatively, full multigrid initialization is also available for some flow cases that allows you to proceed with the second order scheme from the start, but for a simple flow that is aligned with meshes, for example laminar flow in a rectangular duct model with a quadrilateral or hexahedral meshes, or some cases just like in this present CFD simulation of double facet, the numerical diffusion will be naturally low, so you can generally use the first order scheme instead of the second order scheme without any significant loss of accuracy. Finally, if you run into convergence difficulties with the second order scheme, you should try the first order scheme instead. Setting under relaxation factors, we should say that the pressure-based solver uses under relaxation of equations to control the update of computed variables at each iteration. In ANSYS Fluent, the default under relaxation parameters for all variables are set to values that are near optimal for the largest possible number of cases. These values are suitable for many problems, but for some particularly nonlinear problems, for example, some turbulent flows or high Rayleigh number, natural convection problems, it is prudent to reduce the under relaxation factors initially. It is good practice to begin calculation using the default under relaxation factors. If the residuals continue to increase after the first 4 or 5 iterations, you should reduce the under relaxation factors. Occasionally, you may make changes in the under relaxation factors and resume your calculation, only to find that the residuals begin to increase. This often results from increasing the under relaxation factors too much. A cautious approach is to save a data file before making any change to the under relaxation factors and to give the solution algorithm a few iterations to adjust to the new parameters. Typically, an increase in the under relaxation factors bring about a slight increase in the residuals, but these increases usually disappear as the solution progresses. If the residuals jumped by a few orders of magnitudes, you should consider halting the calculation and returning to the last good data file saved. You can use the residual monitors dialog box to control the residual information that Fluent software reports. In the equations section, the residual option indicates the name of each variable for which residual information is available. And the monitor indicates whether or not the residuals for each variable are to be monitored. You can toggle monitoring on and off for each variable by turning the corresponding checkbox in the monitor list on or off. The check convergence option indicates whether or not the convergence of each variable is to be monitored. If convergence is being monitored, the solution will stop automatically when each variable meets its specified convergence criterion. You can check convergence only for variables for which you are monitoring residuals. You can toggle convergence checking on and off for each variable by turning the corresponding checkbox in the check convergent list on or off. And finally, the absolute criteria or relative criteria shows the residual value for which the solution of each variable will be considered to be converged. To set this value, manually enter the new value in the corresponding absolute criteria field. And that's it. The standard initialization method has been selected, and also the initial values are computed from inlet zone. As it's obvious, the Y velocity is equal to 30 meters per second. The number of iteration is equal to 600. That seems sufficient for the CFD simulation. Just click on the calculate button to start the solution. For displaying every desired contour, the first step is to defining a plane that is appropriate to displaying all the two-dimensional contour on that. So the best two-dimensional plane for the contours will be the plane that passes exactly from the middle of the UAV. So by following this way, we can make this plane. Here is the pressure contour, and as it is obvious, the maximum pressure occurs in colliding the wind flow of the front of the UAV and also somehow in the window location of the UAV. As we can see, the maximum velocity magnitude is even more than the inlet velocity. The inlet velocity was 30 meters per second, while the maximum velocity in this plane shows the velocity more than 40 meters per second that occurs at the top of the UAV. The maximum turbulence occurs at the front of the UAV and also at the back of the UAV because of the colliding the wind flow with the UAV, and also the phenomena like vortexes and wake. Following this way, we can check the drag force and also drag coefficient in the Y direction, and also by changing the direction from Y to Z direction, we can obtain the lift force and also lift coefficient. And finally, from the vector section, we can see and display the vector and the selected plane that we have made before, and we can see the vortexes and also velocity magnitudes, and it's so clear. The applied settings are summarized in the following tables as a review. To benefit from Master CFD services, including simulation, consultation, and training, contact our experts via info@mastercfd.com.